We're now going to discuss the topic of exponential functions. So I have an example to kick off this topic here. We're going to create a table and graph the functions 1/3 to the x, 1/2 to the x, 3 to the x, and 2 to the x. Now just as a quick example, if I was doing something like f of, 3, so f of 3 would be 1/3 to the third power. By properties of exponents, this is 1 to the third power over 3 to the third power, which is 1 times 1 times 1, all divided by 3 times 3 times 3, which is then 1/27th, which as a decimal is 0.037, repeating. A lot of these function evaluations you can do by hand like this. There are some that you can't. So for example, if you wanted to do f of 1/2, then f of 1/2, that's equal to 1/3 to the 1/2 power. And when you raise to the 1/2 power, that gives you 1 over, we can do, first I guess we can apply the rules of exponents. So this is 1 to the 1/2 over 3 to the 1/2. And raising to the 1/2 means take the square root. And so this is square root of 1 over the square root of 3. The square root of 1 you can actually compute by hand. That's just 1. And the square root of 3, we can't compute this by hand. We'll need to use a calculator. And this ends up being about 0.577. Let's do one more example of evaluating f by hand. So if you wanted to do something f of minus 2, then this would be equal to 1 over 3 to the -2 power. And we can use the rules of exponents to get this is 1 to the -2 over 3 to the -2. And now when you raise something to a negative power, you can move it, or you can flip it and change to a positive power. So this is 3 to the +2 over 1 to the +2, which is just equal to 9. Let's do one final example. I may have lied that this previous one was the last example that I do of evaluating these types of functions. So let's do f of 2/3. So this is all right, we have our base 1/3. So this is going to be 1/3 to the 2/3 power. So this is 1 to the 2/3 divided by 3 to the 2/3. And 3 to the 2/3, what this means is 3 to the 2/3 equals the cubed root of 3 squared. That should be a 2. And this ends up being approximately 0.481. And if the cubed root, so the cubed root of 3 is not a rational number, but if you had something here that the cubed root of some number was a rational number, then you could do this computation by hand. It's probably more meaningful to show you an example of what I mean. So 27 to the 2/3. This is equal to the cubed root of 27 squared. And the cubed root of 27 is 3. That's because 3 times 3 times 3 is equal to 27. So this is equal to 3 squared, which is 9. So there are some values of where you raise it to the 2/3 power, or in general some fractional power, and you can compute that by hand. Now let's go onward to creating a table and graphing these functions. So I'm going to create a table, well I already have, with the x values from -2 to 2. You could do more if you want, but it's not necessary. And I'm going to plug in all these x values to all of these functions that are listed here. And let's go ahead and fill in this first row here. So we already did 1/3 to the -2 power, and we found that to be 9. And 1/2 to the negative 2 power, well, that's just going to give me 1/2 to the minus 2. That's equal to 1 to the minus 2 over 2 to the minus 2, which is 2 squared over 1 squared, which is 4. So this is going to be 4. I'm not going to go through all of these calculations like this, but I'll do, let's say, a couple, let's say for the first row here. Now, 2 to the minus 2, that's equal to 1 over 2 squared, which is 1/4. And then 3 to the minus 2 is equal to 1 over 3 squared, which is 1/9. Now I'm not going to make you watch me do these calculations over and over again. If you want to go ahead and fill in the rest of this table as a practice, go ahead and pause the video and do that. If not, the completed table looks something like this. So a couple observations. All of these functions are the same at x equals 0. They're all equal to 1. Couple other or maybe one other observations. 3 to the x starts at 1/9, and 1/3 to the x ends at 1/9. And if you travel from top to bottom on 3 to the x, and then from bottom to top on 1/3 to the x, you see that this lists all the same values. There's a reason for that. The reason is because if you take 1/3 to the x power, you can write that as 1 over 3 to the x. And this is equal to 3 to the minus x because, well, if you have a power in the denominator, you can move it to the numerator at the cost of putting a negative. Let's go ahead and graph these on some graph paper here. So I have my axes set up down here, and they're set up in a particular way. The x scaling is much larger than the y scaling because if you look back to my table, I'm going to need all the way to y equals 9, but I only need to x equals 2. So that means I'm going to have my x scaling be much larger than my y scaling. And you'll also notice that I don't have any negative numbers because, or negative y values that is, because, well, none of the y values are negative. So let's go ahead and graph these. Let's do 1/3 to the x first. At x equals -2, the y value is +9. At x equals -1, the y value is +3. At x equals 0, the y value is 0. At x equals 1, the y value is 1/3. And at x equals 2, the y value is 27. And I can connect these with a smooth curve to sketch the graph. All right, so I estimated as best as I could down here. 1/3 is less than 1/2, so I put 1/3 below 1/2, and 1/27, well, that's practically 0. My suggestion is to go ahead and graph the other ones on your own. I'm going to fill them in right now, but if you want to pause the video and graph them on your own and then double check with mine, I advise to go do that. And if you did, hopefully your graphs look something like this. These graphs were created just by taking all the points that I have here, the xy coordinates, and plotting them, and then connecting with a smooth curve. So let's go ahead and make some observations here. First of all, I think before I make any observations, I actually want to make a definition. So if a is a positive number, we call a to the x an exponential function, and we call a the base. So in this green example here, 1/3 to the x, the base is 1/3. In the blue example, the base is 1/2, and the bases for 2 to the x and 3 to the x are 2 and 3 respectively. We don't work with bases which are negative. Now with that definition stated, let's go ahead and examine some of the properties of these exponential functions. The first property that I'll note is for these exponential functions, 2 to the x and 3 to the x, as the x values get larger, the y values get very, very large. So for example, if you do a computation such as 3 to the, I don't know, 10th power, this is equal to 59,049, which is quite large. So as the x's get larger, the y values get very, very large. In a similar vein, as the x values get really small, that is really negative, so something like x equals negative 500, these functions get really close to 0. So if you do something like 3 to the minus 10, that's 1 divided by 3 to the 10th, which after substituting into a calculator, I get something like 0.000017. We'll contrast this behavior to the behavior of these other two functions in a moment. Let's go ahead and write down these properties that we've investigated. And I guess before we write it down, we have to identify what characteristic makes the behavior of these two functions that I've circled, 2 to the x and 3 to the x, different than these two functions which I have not circled, 1/3 to the x and 1/2 to the x. Well, the characteristic is that the base is larger than 1. Okay, so let's go ahead and make a list here of some exponential function properties. And the first is that if the base is larger than 1, if the base is greater than 1, then as x gets large, the y values get large. So the y values, which is a to the x, gets large. And we have a mathematical shorthand for this statement. So mathematically, we might say as x goes to infinity, so as x gets large, the y values, a to the x, also go to infinity. Now, as x is going to minus infinity, so this means the x values are getting more and more negative, the y values for a to the x go to, well, they get really, really close to 0. Now what about the other functions? So 1/2 and to the x and 1/3 to the x. Well, these have bases which are between 0 and 1. So let's just go ahead and copy this whole thing here, because we're just going to make some modifications. So if a is between 0 and 1, then as the x values get larger, the y values are getting closer to 0. So then as x gets large, y equals a to the x gets close to 0. The mathematical shorthand for this is as x goes to infinity, y goes to 0, and also as x goes to minus infinity, we know that from our drawing here, as x goes to minus infinity, the y values are getting larger and larger, so the y values are going to infinity. Let's write down a couple more properties. So for any exponential function, so doesn't matter what a is, a to the x is greater than or equal to, or strictly greater than 0 for all x. We see that in our graph. We never get a negative output for something like 2 to the x or 1/2 to the x. We can get something very, very close to 0. So for example, 3 to the minus 10 is very, very close to 0, but we never actually get 0. Okay, so a to the x is greater than 0 for all x, and the graph, the other observation I want to make is the graph of a to the x, this passes through the point 0, 1, goes through the point 0, comma 1 for all x, since anything raised to the 0 power is equal to 1. A to the 0 power is equal to 1.